let's do it. So we're talking about analytic functions. Analytic functions, differentiable, complex differentiable functions. And one thing we want to talk about first is something called a conformal map. Okay. So who can tell me what a conformal map is? What is, if you've read the material, take a look at the material. Can anyone give me an idea? Does anyone have a sense of what a conformal map is or what it does? What? No? Yeah, that's okay. Yeah. Preserves angles? Yeah, that's basically what it does. Let me give the sort of long-winded definition that the text gives. So you have some map. You have some map, and there exists some angle theta and some number r. There exists some number r, so that such that for any curve gamma that goes into E, such that when gamma passes through some point z naught, so this is going to be the definition of a map that is conformal at z naught. So this guy's going to be conformal at z naught. What we're saying is that if you have any curve that passes through z naught at that time, and which is differentiable at 0 with gamma, with the derivative not being 0 there. So if there exists a theta and an r, so that for any such curves, one has that the composition is differentiable at 0 to the argument of f composed with gamma prime at 0 equals the argument of gamma prime at 0 plus theta mod z prime. And 3, the modulus of f composed with gamma prime at 0 equals r times gamma prime at 0. Then we say f is conformal at z naught.
I'm sorry, are these all more conditions, or are they things you get from what you wrote in the lab?
So you're asking what the grammar is, right?
Yeah.
If there exists a theta and an r, such that for all curves this happens. Okay. If there exists a gamma and an r, such that for all curves with these properties, one has these consequences, then we say f is conformal at z naught. One of the consequences of, like Holmes said, one of the consequences of this is that if you have two angles, if you have two curves, that are going through z naught, then what happens to the tangent vectors there is that they just get rotated. They just get rotated by they both get rotated by some theta. The tangent vectors will both get rotated by the same theta, and so the angle between the curves is going to remain constant. Okay, so any curves that are passing through Z, if you map them through F, then it'll end up with you end up with the same angle, but the curves will you end up with the same angle at the image point. Okay, that's what this is saying. So this is what this is a definition of conformal map. So consequence of the definition is that angles are preserved. Okay, and it's an easy matter to see that if f is differentiable and f prime of z is not equal to 0, then f is conformal at z naught with theta being the argument of f prime z naught and r being the magnitude of f prime z naught. Okay. So tangent vectors get stretched. What this is saying is that the tangent vector gets rotated by some angle, and what the second one is saying is that the tangent vectors get stretched by get magnified by some r. And that can involve a flip as well, right? But the magnitude is multiplied by some r. Okay. And the proof of this is trivial. It's just the chain rule, right? F analytic implies that f composed with gamma is differentiable at 0. With the derivative is going to be f prime gamma 0 gamma prime 0. That's to say f prime z naught times gamma prime z naught. Gamma prime, sorry, f prime z naught gamma prime 0. Right. So it's trivial, right? The argument of this is just going to be the argument of this product. The argument of a product is just the sum of the arguments. The argument of a product is just the sum of the arguments, right? And so that gives you property number 2, right? And then taking absolute values shows you that your r is going to be the magnitude of f prime. That's enough. Okay. So differentiable implies that you're conformal. Okay. All right. So this gives us an initial idea of how differentiable functions behave. Okay. Just one property. Everyone all right? Everyone all right? So now things start to get a little interesting, I hope. A little bit more interesting. We'll talk about the so-called Cauchy-Riemann functions. Somebody did invent some sort of chalk machine that puts little pieces of chalk back into big pieces of chalk. You make a few dollars maybe. I don't think you make that much money. Right? It's probably cheaper just to buy some more chalk. Okay, so here's the important theorem. You have some function. Let's say f is some complex function. F of z is u of xy plus I v xy. Right, z is x plus I. So here's your if f is differentiable at z naught, then one has a relation between the partials of u and v, namely u of x has to be dy, and u of y has to be negative dx. So being differentiable forces this pair of differential equations on the component functions. So your component functions have to satisfy this pair of differential equations. Okay. This turns out to be So for example, if the Cauchy-Riemann equations aren't satisfying, then you know your function's not going to be differentiable there, right? So for example, so you have a test for non-differentiability. If we look back at this function, remember we saw that this function was not differentiable anywhere except the origin, right? And you can check that, right? You see, well, look, ux is 2x, vy, vy is 0, right? Vy is 0, uy is 2y, and negative dx is also 0. Right? There's no imaginary part to this function. The v is 0. This is the u. Right? And so you see, the only place where differentiability is possible is when x is 0 and y is 0. Right? At any other place, the Cauchy-Riemann equations aren't satisfied. So we know, instantly we know, not differentiable at anywhere except maybe x, y, and z. Now you might wonder, can we tell from looking at it? Can we say, oh, the Cauchy-Riemann equations are satisfied at 0, right? At 0, 0, the Cauchy-Riemann equations are satisfied. Can we immediately deduce that the function is complex differentiable there? And the answer is not quite, but almost. Not quite, but almost. So differentiability implies that the Cauchy-Riemann equations are satisfied, but it's not quite true that the converse is not quite true. But it's almost true. So just for your amusement, let me put up a theorem that was in the graduate text that we used when we took our complex analysis at the University of Chicago, my first year of graduate school. So this is from R. Simmons' complex analysis on known variable. And this is sort of like the ultimate, get as much out of nothing as possible. So like with as little material as possible, he tries to, he basically gets the great results of, with as little. By introducing as little as possible, he managed to get a lot of great results. Anyway, it's extremely concise, and we don't use it in this course, of course. But one result that is proved in that text is called the Riemann-Markov theorem. I don't know boundless. But it's like the ultimate converse of the of this theorem. So if f is continuous on an open set, and the partials exist and satisfy Cauchy-Riemann equations, then f is differentiable. Okay, so that's pretty awesome, I'd say. Like, all you need is, in fact, all you need is continuity of the function. As long as your function is continuous and the Cauchy-Riemann equations are satisfied, then your function is complex differentiable. Okay, so this is at least to my knowledge, probably the strongest converse to this statement. Okay, we will prove some weaker versions of that. We're not going to prove the Luhmann-Menkoff theorem, but we'll prove some partial converses. Okay. So, like in the text, they give that a function being complex differentiable is equivalent to the function being real differentiable and satisfying the Cauchy-Riemann equations. Right? Being real differentiable and satisfying the Cauchy-Riemann equations. But that's a lot weaker than this. Okay. Yeah.
Why doesn't that make that into a real here?
Well, because so if your function is differentiable there, then the Cauchy-Riemann equations are satisfied. But it's not true that if the Cauchy-Riemann equations are satisfied, then they're differentiable. Right? What that's saying is that if your function is continuous and the Cauchy-Riemann equations are satisfied, then yeah. So putting them together, it would be saying f is continuous. Say f is continuous. Then you have f is differentiable if and only if and only if the Cauchy-Riemann equations are satisfied. Okay, so that's what this says. Putting them together. Okay, so for example, actually we can say, if we wanted to, we could say by Luhmann-Menkoff, the fact that these things are differentiable. Well, no, wait a second. No, I'm sorry. This has to occur on some open set, so we couldn't use Luhmann-Menkoff. I was being greedy. No, I'll erase it out of embarrassment. Okay, so Cauchy-Riemann equations. Does anyone know the proof of it? There's just one trick to the proof. I should make you guys read the book. Okay, so one of you guys you never read your book. So there's only one trick to it, and that is differentiable means that this particular limit exists. And then what we're going to do is just look at the limit as we take the difference being a real difference, and we take the difference being real and the difference being imaginary. We played this kind of trick last time, and that's basically the same trick that we're going to play now. So proof, just compare the values of the limit as zeta goes to 0 along the different axes, along the real and imaginary axes. Okay, so here we go. The limit exists, right? This derivative exists. That means that this limit f of z naught plus zeta minus f of z naught over h, whoops, after this, over zeta, as zeta goes to 0, exists, right, and equals this thing. Okay. So the limit existing should mean that if we take a real number, so let h be a real number, and we examine that limit, right, then that is going to be the same as this limit, right? So when we write it out, this is going to be u of x naught plus h, comma y naught, plus iv x naught plus h, comma y naught, minus u of x naught y naught, minus iv x naught y naught, over h. Okay. So I just wrote the same thing, expanded out, but we're taking our difference to be a real number. Right? We're taking zeta to be a real number. Right? But then you see what that is, right? What is that? As h goes to 0, well, you're just going to get u sub x, right? You're going to get the partial of u with respect to x at x naught. Right? Partial of u with respect to x at x naught, y naught. Right? Plus iv partial with respect to x at x naught, y naught. Right? And similarly, right, we do the other part of it. Right, if we take our difference in the second variable, right, so it's going to be limit as h goes to 0 of u x naught y naught plus h plus iv x naught y naught plus h minus u x naught y naught minus iv x naught y naught over ih. Right, so you're taking your zeta, here we're taking our zeta to be ih. Take your zeta to be imaginary. Right. Taking this zeta corresponds to taking a difference in the second variable. Right. Okay. And so what you end up with here is you see it's going to be u sub y at x naught y naught plus iv sub y x naught y naught, everything over I. Right? Which is the same thing as vy x naught y naught minus I vy x naught y naught. Okay, so it's not that exciting, but you see that those things have to be equal to each other, and so v sub x must be v sub y, and v sub x must be negative v sub y. By comparison. Okay, any questions? Any questions? Any questions? Okay. Just a couple of comments. Right, so that's the end of the proof. But let me make a couple of comments. First, notice that we saw that v prime z was ux plus idx, right? We also saw that v prime was v sub y minus I v sub y. That's what we just did. And we could write this, if we wanted, as the partial of f with respect to x. Right? F was u plus I. You can think of this as the partial of f with respect to x. And this thing here is 1 over I, the partial of f with respect to y. Whatever I times the partial of f with respect to y. Right. So another way that people write the Cauchy-Riemann equations. So the Cauchy-Riemann equations could just as well be written in this way: partial f with respect to x equals 1 over I partial of f with respect to y. Along the same lines, sort of along the same lines, number 2, notice that, well, x you can think of as z plus z bar over 2, right? Right, remember, z is x plus iy, z bar is x minus iy. Right? So x is z plus z bar over 2, right? And y is z minus z bar over 2, I, over 2i. And so it makes sense to define df dz as 1/2 df dz plus 1 over I df dy. That should be an x. Right. Right, by the chain rule. By the chain rule. Right. You can take, if you're taking the partial with respect to z, then you're going to take, the partial. You see what I mean? Okay. So and it makes sense also to define df dz bar as 1/2 df dx, sorry, minus 1 over I df dy. Again by the chain rule. So from that point of view, what you have then is that f analytic, then f prime is df dz. Right? Because you're taking 1/2 of df dx plus 1/2 of 1 over I df dy. But each of those halves is half of f prime. Right? So you add them together, you get back f prime. df dz is going to be f prime. Yeah.
Since f is a function of z, shouldn't that not be a partial? Shouldn't that just be f prime? It seems like it just boils down to f prime.
Yeah, so, but in this case, you're thinking of f as a function of z and z bar, as a function of z and also of z bar. Okay, so it makes sense to rather think of it as,
okay.
Right, you're taking derivative with respect to z or the derivative with respect to z bar. So that's why, yes?
Sorry, for number 1, are those 1 over i's or I over i's?
1 over I. They definitely wouldn't be I over I. Okay. And what further, what do you see? That df bar, if f is analytic, then df dx over 1, I'm sorry, df dx equals 1 over I df dy. So this is actually 0. So this gives you another way of thinking about analyticity, right? It means that your derivative with respect to z bar is 0. Okay, you're a function of z, but not z bar. Your pure function is z. Okay. So let me, let's now go for one of the converse results to the previous one. Okay. So here's one. This is not the one in the book, but it's sort of similar to it, but the approach is different. So suppose df dx, df dy exist and satisfy df dx equals negative I df dy. That's the Cauchy-Riemann equations. Okay, one version of the Cauchy-Riemann equations. If df dx, df dy are continuous on omega, then f is complex differentiable. So satisfying the Cauchy-Riemann equations and continuity of the partials will give you differentiability. Okay. I'm trying to think of some way to liven this up for you, but I don't think there's anything. So just, okay, anyway. So let's show it. So let's let f be u plus id. Let a be alpha plus id be some point in omega. And we want to show that the limit of f of a is zeta minus f of a over zeta exists as it exists now. Okay. Let's notate let zeta be written as xc plus I eta. C plus I eta. This is C. This is eta. I had to get used to them. You have to get used to them. And that is, I had to learn how to write them. You have to learn how to write them. So, in fact, probably I'm writing them incorrectly. If there are any people who are in classics, once I had a student in classics, and she said, "That's not how you write it." But zeta c. Okay.
It's like the alpha game joke.
Yeah. Yeah, I should just stick with zetas and x's and gain my fame that way. Yeah. Anyway, if you don't like to write xc, then just write some sort of scribble, okay? with many wiggles as opposed to one big wiggle. I did for some years before I learned how to write it properly. Anyway, these are common variables. Okay, so okay, so we want to show that this limit exists. Let's do it. Let's consider the top f of a plus zeta minus f of a. We observe that u of a plus zeta minus u of a we can write as u of alpha plus c comma beta plus zeta minus u of alpha beta. So we're just switching over to the real variables. Okay, that's all we're doing. Okay. And then we use a multivariable Taylor's theorem. So Taylor's theorem tells us will tell us about this difference in terms of the derivatives. Okay, so this by Taylor's theorem is a partial of u with respect to x at alpha beta times c plus the partial of u with respect to y at alpha beta times eta plus some error. Plus some error function. Okay. Where the limit as c and eta go to 0 of this error function over the magnitude of c plus the magnitude of eta is 0. Just think of your one variable Taylor function, right? You can approximate the change. You can approximate the change with some by the derivative times the distance, right? You approximate the change with the derivative times the distance plus some error that vanishes as you get closer, as the change gets arbitrarily small. So that's all we're saying. Okay, and similarly, so I tried to get more chalk from the dance department, but they don't use chalk in the dance department, and they ended up digging around in the back, and they came up with this piece of this box of chalk that said 29 cents on it. I figured it was from the 60s or 70s, and it was probably that kind of chalk that gives you cancer. So it's still in my office. I'm trying to sell it on eBay. Anyway, so that's why I don't have chalk today. I'll get some chalk next time. Okay, so similarly, b of a plus zeta minus b of a, we can express in the same sort of way. Right? db dx alpha beta times c plus dv dy alpha beta dot beta plus some other error with the same sort of decay. So then, if we look at f of a plus zeta, and here's where the Cauchy-Riemann equations come into. Right? We haven't used the Cauchy-Riemann equations yet. We have that this minus this is u a plus zeta plus iv a plus zeta minus u of a minus iv a. What that if you write that in terms of df dx, that's going to be df dx times c plus df dy dot eta plus this error. right? Remember, F is U plus E plus IB. So you get this. And now you invoke the Cauchy-Riemann equations. Right? You say that this is df dx alpha beta dot c plus I df dx alpha beta dot beta plus the error. Right, because then make a mistake. Df dy by df dx is going to be then make a mistake.
You multiply both sides by I, is that okay?
Yeah, I'm sorry, that's right. Yeah, sorry. The mistake is that I thought I made a mistake. So yeah, that's right. Yeah. Okay, so by Cauchy-Riemann equations, these are the same thing. Where, so this is, so let me write it up here, sorry. So we end up with f of a plus theta equals df dx alpha beta times c plus I beta plus this error term where this error goes to 0 as zeta goes to 0. Okay, and then dividing both sides by zeta, you end up with what you hope for. You end up with df dx alpha beta plus the limit at zeta goes to 0 of epsilon zeta over zeta, right, which is 0, which is 0. And so the function is differentiable, and the derivative turns out to be df dx, which is what it should be. So limit exists. So f prime a exists and equals df dx as it ought to. Okay, so we're not, although we don't prove the the great Riemann make-off theorem, we do get this converse. Okay, everyone all right with the converse? Any questions? Any questions? Okay, in that case, let's just go on. Upwards and onwards. And one of my professors at Princeton was this old guy, and he would always use terms like hither, thither, and yon, and upwards and onwards. And there's, oh, upwards and onwards, you know. But, he was a really amazing lecturer. He'd come in, I probably told this story before, but he'd come in and he's a cheerful guy, old man, but very cheerful. He was apparently one of the only people who ever got tenure at Princeton. That is, most of the time, Princeton will hire an assistant professor, and then after 6 years, they kick them out. Yeah, they fire them, and then after 6 years, they kick them out. They never give tenure. They never promote people to tenure. They never give them tenure or let them stay. But I heard that he was maybe like one of the only people that it ever happened. Yes.
Is that still true at Princeton?
I don't know. It was when I was there. Although one person when I was there actually did get tenure. It was Kurt McMullen, who was this really, really passionate guy. He'd come in, so I just ran on the board as fast as possible. I tried to emulate him in my speed of writing, but anyway, he was an incredible lecturer and a brilliant mathematician. He was granted tenure, and then soon after that was awarded the Fields Medal. Right. So it's this sort of person, Nobel, basically equivalent of a Nobel Prize winner who can get tenure at Princeton. Anyway, so this other fellow, Robert Gunning, the older guy, would come in. He'd look at the board from the previous class, and then he'd just erase parts of the board. He'd say, leave this graph here, and he'd leave some equality here, and then he'd start lecturing from the left side of the board. And then, as he got to the graph, he'd work it into his lecture. He'd make it relevant to what he was talking about, and then he'd get to this point, make it relevant to what he was talking about, just for the fun of it. I wish I could do that, but no. Yeah, I don't have such improvisational skill. But set your sights high. Yeah, we'd always cheer when he did it. Yeah. Okay. Okay. So, sorry to go back to my sort of dull way of lecturing. Complex. At least I can tell you that there are great lecturers out there. Complex differentiability versus real differentiability. Yeah, McMullen actually was a graduate of Williams College. He got his undergraduate from Williams, and then his graduate he did in France, I think. But anyway, his teaching was very similar to, I think, it was very different from the other professors at Princeton, probably because of his liberal arts background. Okay, complex differentiability versus real differentiability. Okay, so let's see what's going on. You can make some connections that are kind of interesting. So recall real differentiability. If you have a function from R2 to R2. And let's say that R2, the function, has component functions u and v. Okay. We say f is differentiable, is real differentiable at some point p naught in R2, of course. If there exists a linear transformation J from R2 to R2, such that f of p naught plus h minus f of p naught minus j of h over the normal of h tends to 0. Okay, so as the limit as h goes to 0 is 0. That's what differentiability means. You may have never seen this if you haven't taken a course Yeah, this is how we like to define differentiability in multivariable calculus, but we often don't because it involves the word linear transformation, and we don't require Math 60 linear algebra as a prerequisite. If we did, this is how we would define it. Okay, so being differentiable means that your difference, right? The difference is well approximated by a linear transformation. Right? The difference, the change of your function, right? The change between these 2 points is well approximated by a linear transformation on this h. Okay. I mean, you can think of this as saying that f of p naught plus h is basically f of p naught plus jh. Right? So it's something like your tangent line formula, tangent line approximation. Right? If you remember the tangent line approximation, right? F of x naught plus h is basically f of x naught plus f prime x naught h. Right? That's your tangent line approximation of your differentiable function. Right? So this is basically that. And further, if f is differentiable at p naught, then the j at p naught, the j there is actually going to be is going to be this matrix, partial of u, partial of x, partial of u, partial with respect to y, partial of v with respect to x, partial of v with respect to y, which is called the Jacobian matrix. So, like I just said, in other words, f of x y minus f of x naught y naught is well approximated by this matrix ux, uy, u sub x, u sub y, v sub x, v sub y, times x minus x naught, y minus y naught. If you're differentiable, then the change is approximated by this. Okay. So now, if f u plus ib is, so this function here, we're also going to think of as a function on the complex plane. Right? As a function on the complex plane, little f being u plus ib. Okay? It corresponds exactly to this real function, f being u and v, of u and v. Now, if this thing is complex differentiable, then what does that say? That says that u and v satisfy the Cauchy-Riemann equations. So we have ux equals uy and uy equals negative x. Right. And so ux equals vy and uy equals negative vx. Right. uy equals negative. So these are equal and these are negatives of each other. Right. So it's not a symmetric matrix, but it's what's called a skew symmetric matrix. Right? So the space of F is a skew symmetric matrix. further, if we look at the modulus of the derivative, this is not surprising, ux plus I dx, dx minus I dx, ux squared plus dx squared, which is the using, again, the Cauchy-Riemann equations. This is going to be ux vy minus ux uy dx, uy dx, which is the determinant of the above matrix. So this is sort of common. So the linear transformation that expresses the change, right? That approximates the change of your function is a skew-symmetric matrix. And you remember that recall that multiplication by a skew-symmetric matrix corresponds to complex multiplication. Right? Corresponds. This is something we observed early on, that you can embed the complex numbers in the skew-symmetric matrices. In fact, so it's going to correspond to, so JF corresponds to multiplication by some complex number, namely ux plus I dx, which is f prime z naught. So being differentiable is basically saying that your functions, the change of your function is corresponds to multiplication by a complex number. The change of your function corresponds to multiplication by a complex number. Right? And if the Cauchy-Riemann equations aren't satisfied, then the multiplication that occurs, it's some linear transformation, but it's not one that corresponds to a complex number. Okay. It's a multiplication that doesn't correspond to a complex number. Okay. And that's what happens when the function's not complex differentiable. Right? So you could have a real differentiable function, but it wouldn't be complex differentiable. So with this viewpoint, from this viewpoint, it's easy to see that complex differentiability at z naught implies real differentiability. With J f z naught, the skew-symmetric transformation given by multiplication by f prime z naught to real differentiability plus the Cauchy-Riemann equations implies that this function, this linear transformation that approximates the change of your function corresponds to multiplication by a complex number. And thus gives you complex differentiability. Okay, and so I'm sort of sketching out for you the book's result that f is differentiable at z naught if and only if f is real differentiable at z naught and satisfies this Cauchy-Riemann equations. Just if you want to see it more clearly written out, it's on page 68. But I think this should give you some sense of it. Yeah, Christian.
What I'm not sure if this is something that's easy to answer, but what can you, what sort of transformations can you do with any linear transformation that you can't do with just a complex number?
So the complex numbers are going to correspond, right? What does complex multiplications correspond to? Right? Corresponds to a rotation and a scaling,
Mm-hmm.
right? You see that. You know, what is complex multiplication? It's rotation plus scaling,
Mm-hmm.
right? So you know, any linear transformation that's not rotation plus scaling, we think
A shift.
So the shift is actually because you're looking at the a shift isn't actually a linear transformation.
It's not.
No, because a shift, you know, a linear transformation has to take 0 to 0.
Ah, right.
Right. So a shift isn't it, but yeah, but just any other kind of linear transformation. Shear. So like you're saying,
Like take the unit vectors to what of it from your perspective, like that kind of something?
yeah. Let me think. Give me one more second. Give me a second to think if I can think of anything. Right. So. Sorry, no, I can't think of anything. I was wondering, no, forget it.
Are you looking for something more than like a two-way matrix that isn't skew symmetric?
Yeah, basically. So that's.
I could fill anything in. Right?
Yeah, exactly. So I mean, but that's sort of like, what is that a good answer?
I mean,
Right?
that's just a lot of linear transformations.
Exactly. But you know, what do you say? So yeah, that's so certainly it just is anything other than anything other than those things. But what I think Christian's asking for something
Like a characterization of what can't you get just by adding together rotations and
right.
scales.
Right. Yeah, I don't know offhand. I don't have a good answer for that. I don't have a good description of that. I probably should. So let me just introduce, before we go, let me introduce one last thing for harmonic functions. We'll talk more about these next time. If f is analytic, then what we see is that what we just said is that u sub x equals v sub y, v sub y equals negative v sub x. Right? And so, what does that give you? That gives you that u sub xx equals v sub yx, and u sub yy equals negative x sub xy. Okay. If you take partials with respect to x and partials with respect to y, further, right? Now, then, and this is a little bit fishy, then you see that u sub xx plus u sub yy equals v sub yx minus v sub xy, which under certain conditions, these are the same thing, right? V sub yx and v sub xy are going to be the same thing, so you get 0. So it's a little bit fishy to do this, because you can't just switch the order of partials whenever you feel like it. You have to have some continuity conditions satisfied. But what we'll later see is that those continuity conditions are satisfied. Okay, so this is actually legal, although it looks fishy right now. Okay. And so what you see is that, right, and you also see that vxx plus vyy is also 0 for similar reasons. So both of these things, both u and v satisfy a certain differential equation, or they're both killed by a particular differential operator. One denotes by a delta, this triangle, the second partial with respect to x plus the second partial with respect to y. And this is called the Laplacian. The Laplacian operator. And we say a function is harmonic if its Laplacian is 0. So what we're saying here is that for any analytic function, its component functions are harmonic functions. Right. And so if f equals id is analytic, then u would be a harmonic. And given any u v that satisfy the Cauchy-Riemann equations, one calls v the harmonic conjugate of u. Okay. And the question that is sort of interesting is the following. Suppose you have a harmonic function. Suppose you have a harmonic function u is it always possible to find a V so that when you add IV to U, you get an analytic function? Right? Can you find a function that you can add on to this guy to make it an analytic function? Okay. And that's actually a pretty tough question, and its answer involves something called the Hilbert transform. Which you may never see, but unless you take some more advanced course in complex analysis. But anyway, so we'll talk more about harmonic functions next time. Harmonic functions have their own full